Okay, welcome to this electronic trip units CPD. My name is Alessandro Danieli. I am the offer marketing manager for the power breakers for the United Kingdom. Today we will speak about the different types of trip units you can have on low voltage circuit breakers, and we will focus our attention on the electronic trip units, of course. So on molded case circuit breakers, so on power breakers from 100 amp, even less, up to 3000 amp, we have two different kind of trip units. The first one is the thermomag trip unit, that is the traditional type. This type of trip unit actually is used only in the smaller sizes of molded case breaker. Typically you have this kind of trip unit up to 250 amps. Sometimes you can see also for 500 amps, or even in some cases 800 amp. So I said this is a traditional trip unit because this has been developed in the 50s. Hasn't changed much in the last 60 plus years. So we have two physical elements inside the trip unit. One provides the overload protection and the other one provides the short circuit protection. The first kind of protection, the overload, is called also thermal protection, and the second one is called also magnetic. That's why they are called this way, is because for the thermal protection, so the overload protection, a bimetal is used. So we have a bimetal inside the trip unit. This bimetal is passed by current. The more current is flowing inside the bimetal, the more this element tends to bend. If the current is too much, so it's over threshold for a certain amount of time, the bimetal will bend enough until reaching the tripping mechanism of the breaker. When the tripping mechanism of the breaker is triggered, the breaker will open, and so we have opened for overload by means of a bimetal because of the thermal effect, of course, current equal heat. The other element, so the short circuit protection, is provided with a magnetic type of element. So in this case you have a little anchor inside the trip unit. This anchor is put in place because of a spring, and this anchor is attracted by the electromagnetic field created by the current. If the current is too much, this will overcome the spring, and so the little anchor will be attracted, and this will trigger the open mechanism of the breaker. So inside this trip unit, we don't have any kind of intelligent element. We don't have a microprocessor. We don't have any kind of electronics. In the graph you can see in these slides, you can see the two elements plotted in a time current graph. So the overload element is called also long time, will trip the breaker in some seconds normally, is current inverse. So the more current is flowing into the circuit breaker, the quicker the overload element will react. The other part of the characteristics is the magnetic one. In this case, is current independent. So if we are over threshold, whatever current is passing by, the breaker will trip as fast as possible, and so basically will trip all the time with the same opening time. We can normally, and in the vast majority of the circuit breaker, we can set the thermal element from 70% to 100% the rated current. So if I have a 100 amp molded case circuit breaker, I can set this from 70 amp to 100 amp. Again, in the vast majority of the circuit breakers, we can set the magnetic element between 5 and 10 times the rated current of the breaker. So in this case, if I have 100 amp breaker, I can set the magnetic protection to trip the breaker as soon as possible when the current is over 500 amp, for instance, or maybe when it's over 1000 amps, so 10 times the rated current. The setting of the thermal element are very similar between all manufacturers, so tend to be the same. It's even for the magnetic protection, but in case of the magnetic protection, we can have some special versions of circuit breaker for which we have a low magnetic. So in that case, you can see some circuit breakers that can be set down to 3 times the rated current of the breaker. So what are the advantages of a thermomag trip unit? So thermomag trip units have been the only trip unit up to the 80s, late 80s, when electronic trip units became a viable option. So the advantages are that you are simple to set up, so you need just a screwdriver to move the rotaries, and can be used both in AC and in DC. At least, again, the majority of the breakers with thermomag trip units can be used in alternating current or direct current. There are some disadvantages, well, quite a lot of disadvantages. So they are not very accurate in a way for which, well, two different ways. The first is that they are not actually because of their nature. So because these are analog elements, are quite difficult to be set. So normally this kind of protection function, you have a tolerance of 20%, plus minus 20%. So if we set a circuit breaker at 100 amp, meaning that over 100 amp this breaker needs to open for overload, actually this breaker can be an 80 amp or can be a 120 amp, we don't know. So it's plus minus 20% on everything. And the second point is that these trip units, I mean the overload part of this trip unit, so the bimetal, is temperature dependent because these trip units are calibrated at 35 or 40 degrees Celsius. So if the ambient temperature is 70, for instance, the bimetal starts already bent. The more the current, the more the bimetal bends. But if we start from an ambient temperature that is already hot, the bimetal, it's already bent, at least in part. So it will open before the theoretical threshold that we have chosen. And the same way, well, actually the opposite way is in case we have minus 10. So we are no more at this 35, 40 degrees Celsius, but we are minus 10. In this case, the bimetal is not in the same condition as at 40 degrees Celsius. We can have basic protection only, so you don't really have ground fault, for instance, on this kind of trip units. You don't have residual current protection and so on. So you have only overload and short circuit, as said in the previous slide. These can be used only for limited applications, so you don't have many different type of special trip units. There are special thermomag trip units for generators, that's true, but there are not many different versions of them. We will see later on, but another point is that they tend to behave not very good in discrimination. So it's easier to achieve a good selectivity or discrimination using electronic trip unit instead of using the thermomag. And finally, they don't provide any metering or any communication. So you can't have any metering on these units, and you cannot have any kind of communication on these units. On the other hand, we have electronic trip units. So since the 80s, we have electronic trip units available for low voltage power circuit breakers. There are some advantages on using this unit. We have extended setting range, so you can set, for instance, the overload can be set from 0.4 to 1, the vast majority of the breakers, also from 40%. More accurate setting, so on one end, the trip unit is more accurate as a trip unit, so you don't have anymore the plus minus 20%. Normally you have a plus minus 10% of accuracy, so it's twice as accurate as the thermomag. And on the other hand, there is no influence of the temperature because the electronic components inside the trip unit are not affected by the ambient temperature. So the electronic trip unit works measuring the current flowing in the breaker. This measurement is a true RMS measurement, so measure the root mean square of the current. Doesn't matter if it is at minus 10 degrees Celsius or it is at plus 70 degrees Celsius. Until a maximum limit, of course, these components are meant to work until certain condition. If I put this breaker in an ambient temperature of 100 degrees, most likely I will start having some problems because the electronic components are not designed to work at 100 degrees Celsius. We can have advanced protection settings, so we can have several different types of protections in an electronic trip unit. For instances, we can have ground fault, or we can have residual current protection if we want. We can have selective S protection function and so on. It's easier to get to a good level of discrimination or selectivity using this trip unit. We have different versions for different special applications. So one example is motor protection. We have special trip unit for motor protection application. We can have metering and communication on electronic trip units. So I can have electronic trip units that measures the current, and I can have electronic trip units that communicate via Modbus or Profibus or other kind of protocols. This trip unit can store trip histories and events inside themselves. Then I can access this memory and I can see, for instance, the last trips of the unit, when it happened, how much was the current flowing into the breaker when the trip happened, and so on. I can set this unit from remote using Modbus, for instance. I can set parameters inside if I want, or I can use softwares running on laptops. I can have information about maintenance indicators like contact wear, for instance. So I have an estimation of how much the main contacts are worn. And I can easily test this trip unit. So you will see that in this picture we have a test connector just on the left of the rotaries. So I can connect with a special cable to a laptop, and then I can provide some testing for the trip unit. Or I can do some troubleshooting if needed, of course. There are two different types of electronic trip units. There are electronic trip units without screen, so I can have a microprocessor and an electronic trip unit, but not necessarily I need the screen. Or like in the example here, you can have an electronic trip unit with a small LCD display that will give me some information about, for instance, currents or voltages and so on. A complete electronic trip unit gives us 4 different protection functions. There might be more, but normally you have 4 as a basic set of protection function. We have the long time, the L, so it's the same protection function as provided by the bimeter, so it's an overload. S, it is protection function against short circuit, but delayed, so short time if you want. I is instantaneous, so the protection against short circuit, and the breaker will try to trip as fast as possible. And then we have G, so ground fault protection, protection against current to ground. I already mentioned before that, for instance, you have an extended setting range for the overload from 40% to 100%. We can see that generally speaking also for the S, we can have from 1.5 to 10 times rated current, the I from 1.5 to 15. These are quite standard values you can get, and the ground fault from 20% to 80%. You will see that with retroactive impedance you can also set a time, at least for overload, as protection function in G. So I can decide how much I want to wait before the trip units trip the breaker. For example, here we can say for the S protection function we can delay from 100 milliseconds up to 400 milliseconds. Now we can take a look at the basic protection function. So overload, for instance, is a protection function that will trip the breaker according to the magnitude of the current. So the higher is the current, the quicker is the breaker to open. In our example here, we can see that if this breaker sees 200 amp, the breaker will trip in 25 seconds, but if the breaker sees 300 amp, the breaker will actually trip in about 20 seconds. Okay. Now the ANSI code for this kind of protection function is 51. As a difference with the thermomag trip unit, we have a family of curves we can use. So on a thermomag breaker, you cannot decide any delay on the overload. It is defined, and you have what you have. But here, I can decide how much I want to wait before tripping the breaker. So in my example here, I can decide how much I want the breaker to wait when the current is 6 times the rated current. So say that we have breaker 100 amp. How much I want the overload protection function to wait when the current is 600 amp. I want to wait 3 seconds, or 6, or 9, or 18 maybe. So since the slope of the current is given by the standard, if we define one point with this delay, we have defined one curve, and so we see that we have a possibility of choosing between 4 different curves. So with the S protection function, this is something that we don't have on a thermomag trip unit. So the ANSI code is 51. So the S protection function is a protection against short circuit. So we are looking at higher currents. In this case, instead of tripping the breaker as fast as possible as the magnetic protection of the thermomag, we can set the breaker to wait before opening. So in my example here, we are waiting 100 milliseconds before opening the breaker. One 100 milliseconds is just an example. We can decide also to delay 200, 300, in this example here up to 500 milliseconds. So you see that this function is quite useful to achieve discrimination or selectivity. So if you need to be selective against another breaker, and we have some problems in doing this, we can use the S protection function to delay the upstream breaker for the time that we need, and so we will have only the downstream breaker to open. So the I protection function is the only protection function where you do not set any time, because the breaker will trip as fast as possible. You will see that in my example here, we have the overload curve in orange, we have the instantaneous in light blue, and then we have another little curve in yellow. So beyond the instantaneous protection function, we have also another protection function of the breaker. We can identify as repulsion of the contacts or self-protection of the breakers, depends on the manufacturer. So the idea is that when the current is too much, even the instantaneous protection function or the electronic trip unit is not quick enough, because still we need some tens of milliseconds to process the information coming from the current sensors. And in the case, there is a mechanical device that can be just the repulsion of the contacts of the breaker, or can be something else that will just intervene in a quicker way, not involving the electronic trip unit. So there will be a mechanical function that will open the breaker in that case. Finally, we have the ground fault. So in this case, the current that we see here, this I measured in Ka, that we see here, is no more the current on the free phases, but it's the current to ground. So in this case, we want to protect from current to ground. So if the current to ground is over a certain limit, the breaker will trip. So what the electronic trip unit is doing in this case is to sum the free currents. If you have a free phase breaker, the vectorial sum of the free current must be always 0. If it is not, means that there is some current that is not in the free wires, so it's going somewhere else out of the electrical network, so it's going to ground, and we may want to trip the breaker because this can be dangerous. This can lead to fires, for example. So LSI protection function can be plotted on the same graph. So S protection function, that we have actually two different ways of implementing the S protection function. We can have this, as we have seen before, as a current independent. So whatever is the current, the S protection function will trip always with the same value. We saw before 100 milliseconds, for example, but we can choose if we want to have this as current dependent. So the more current is flowing, the quicker will be the S protection function. I square T on is the way this is called. And then on a separate graph, of course, because it refers to a separate current, we can plot the ground protection. So if we have a 100 amp circuit breaker, this is an example of complete setting. So with an LSIG protection function, which Schneider this would be called a micrologic 6. So we can set the overload at 75 amps, 0.75. We may want to decide that at 600 the current of the breaker, we want to wait 8 seconds before opening. We can set the S protection function at 8 times. So in this case, it will be 600 amp with a permanent delay of 200 milliseconds. And finally, we can set the instantaneous protection function at 12 times the rated current. So in this case, it will be 1200 amp. For the ground fault, in our example, we want to protect from current going to ground. Our limit, our threshold is 50 amps, so 0.5. And we want to wait 0.1 seconds before the breaker opens, to avoid spurious trip, of course. One of the points we touched before at the beginning was the fact that it's easier to achieve selectivity using electronic trip unit. So with a practical example, if we have an NSX 100 amp, and we have a mini breaker IC60L at 32 amp. In this case, the discrimination limit is 1, so up to 1000 amp, only the miniature circuit breaker will open and the NSX 100 will remain closed. If the current is, for instance, 3000 amp, unfortunately both breakers, so the NSX 100 and the miniature circuit breaker, will open at the same time. But if we use the same type of breaker, so an NSX 100 but with an electronic trip unit, and we compare with the same miniature circuit breaker, 32 amp IC60L, we have total discrimination. So for whatever current up to the maximum limit of the miniature circuit breaker, only the downstream breaker, so the mini breaker, will open. Oh, it is quite better than before. If we have a typical low voltage distribution system, we want to do some grading, so we want to achieve some degree of discrimination normally. We do not want a medium voltage to open for any type of faults on the low voltage side. And of course, sometimes it's difficult to achieve discrimination between the medium voltage breaker and the main low voltage breaker, so we need to pay attention between these two breakers. So we have a first example of grading. So we have the medium voltage protection curve reported to the low voltage side. This is the red curve that is identified here as customer TX10/C. What is important for the medium voltage protection? We want the medium voltage protection to protect the transformer. So we want both breaker at the end, the voltage and medium voltage, to open before the breaker reaches its thermal and dynamic limits. Otherwise, the transformer will be damaged by a short circuit, and we don't want this to happen. But also the medium voltage protection relay must remain closed during the inrush of the transformer. So you know that when the primary side of the transformer is closed for energization, the magnetization flux inside the transformer will draw quite a lot of current, and we don't want this current to open the medium voltage relay. And of course, this is respected in this case. The main low voltage breaker in this installation is the green curve, main LV ACB TX1. It's fine enough. There are no overlapping points between low voltage and medium voltage as we want. And the main low voltage circuit breaker has no overlapping points with all the feeders. So we have quite a lot of MCCB here. You see compression house DB43 and so on. So all of these are clearly not overlapping the main ACB low voltage curve, so we are okay. And this MCCB must not trip during the inrush of the motor. So there are a few motors here, for instance, compressor 1-36, for instance, this is a motor. The curve drawn is actually a star delta starting of the motor. We do not want, and this is not going to happen according to this curve, that any of these molded cases will trip during the inrush of the motor. We have a second example here. So we have, again, we have put the medium voltage curve on the low voltage side. This is a blue one, light blue. Same consideration of before. And again, we want to do this grading. So we don't want any breaker to trip if the voltage, not just downstream it. So we said that having electronic trip unit is quite convenient because we have special version for different application. So the most important we have is the motor. So we have special motor trip units that will not trip during the inrush of the motor. We don't really have special trip unit for transformer, but using the standard trip units that we have, normally it's quite easy to reach a good level of discrimination and protect effectively the transformer. We said we can have embedded metering with electronic trip units. That is true. So normally you have trip units, electronic trip units, able to measure currents and voltages and powers and energies and frequency and the power factor and so on. A typical accuracy is 2% for powers and energies. And of course, we can export this information through the communication system, or we can visualize, in case if we want, this information on the LCD screen, if we have an LCD screen. Or we can visualize this information using a monitor, a panel, connected to the trip unit. We said that inside the trip unit there is a lot of information, and we like to access this information, especially if we need to do some troubleshooting or if we need to do some maintenance, predictive or preventive maintenance. So one type of information we may want to have is the contact wear, for instance, but also maybe we're interested in trips and alarm histories, number of operation, how many times the breaker operated, and all of the kind. Again, for what concerns the measurement, we said we can have this measurement on the LCD display or on a local display if we want. We can export this information through a BMS, building management system, or an EMS, or a PLC, whatever, using the communication. And we will need, of course, the Modbus map of the device. Two things more about the electronic trip units. One thing is that it's quite easy to measure the earth fault loop impedance when we have an electronic trip unit. So if you have an electronic trip unit and the S protection function is set, we want to know what is the impedance of the fault loop. So we will have to divide the voltage by the current to get an impedance. So say in my example, the voltage to ground is 230 volt. Actually, to do this calculation, you should be considering also C mean, that is 0.95. But anyway, I mean, well, because we want to have also some tolerance on the voltage, but okay, for my example, I will just keep 230 volt for the moment. We want to know what is the minimum current that will trip the breaker. So in my example here, if we take a 100 amp molded case circuit breaker set at 0.95, and we set the S protection threshold as 5, we have a tolerance, maximum tolerance of 10%. So if we multiply 95 amp multiplied by 5, multiplied by an extra 10% to take into account the tolerance, we know that we are sure that if we have at least 522.5 amp, this will be enough to trip the breaker. Of course, the breaker will trip even if we have 900 amp, for instance, but this is the minimum current that for sure will trip the breaker. And so voltage divided by this current will give me the earth fault loop impedance at 0.44 ohms, again, not considering my example C mean. Another interesting thing, I guess, about the electronic trip units are the power losses. This is sometimes overlooked, but it's quite important sometimes. So the thermomag trip units have a bimetal inside. So the more current is flowing into the bimetal, the more heat is going out. But the electronic trip units, they don't have any bimetal. So even if we are speaking about the same physical breaker, the power losses tend to be quite less. So for instance, and from these charts, if we have an NSX 160 amp, the power dissipation per pole for the thermomag is 13.95 watt. So every pole dissipates almost 14 watts. But an NSX 160 amp with an electronic trip unit will dissipate, each pole of this device will dissipate only 9.16 watts. So this is about 50% better. And that's it. So we have spoken about the thermomag trip unit and the electronic trip unit, the main difference, and what are the main advantages of using the electronic trip unit. Thank you for your attention and have a nice day. Thank you.